We're currently running a 8 ohm ballasted field from a 7 volt regulated power supply. As we see, let's set our clock. What's going on here? We have 5.5 volts on phase 1 with the resonant rise fluctuating between 51 and 48 volts. On phase 2, we have 6.1, 6.2 volts, 5.9 if I can see that. Everything's fluctuating to a great degree. And on phase 3, we have 5.1 volts, 4.8 fluctuating to a great degree. Over here, we're going to look at our stator line amperages and our phase amperages. We have no loads on the system. The checkering scheme there shows that from the view of the top, each segment of segmented coils wrapped by black tape is interwoven in a spiral. One goes counterclockwise down, 2 goes counterclockwise down, and 3 goes counterclockwise down. When we put a load on the system, that will inhibit the vibration of the phase involved. But for now, we're going to look at the unloaded state of the system. And by comparing our stator line amperages, taking an instantaneous photograph because of the cyclic activity, we can figure the phase angles by the law of cosines. We can also figure the phase angles by the relative voltages that each phase requires. And on phase 1 we have 50 volts from 5.5, Q of 10, outs there. On phase 2 we have 6.1 volts internally being compressed to 43 volts in fluctuation. And on phase 3 we have 5.1 volts in fluctuation, enabling a compression of 47 volts. So these are all Q factors in the vicinity near 10. Now we have 43 volts in fluctuation there, and we have 47 volts in fluctuation there. And down here we have a meter reading 75 volts between those two phases, 2 and 3. To run our bipolar Tesla coil system then, seems most logical that we would use phases 2 and 3 to procure the power, since that is the widest phase angle that we can observe from the input voltage readings to the output voltage readings. They're close in time to each other. They could be about 120 degrees, but later on we can determine that. Now, on this system then, we have subsidiary inductors. To the right are 2 high induction coils with a Krypton bulb in the back and a Xenon bulb in the front to be placed as loads. And we also have a 3rd inductor over there. What we're going to do now is we're going to load down the system by placing 1 inductor at a time on the system and note the results with our inputs. As we formerly noted, the phase that we draw on will be reduced in vibration. And we always find that from the top view that the phase that gets loaded down will always be the phase in the middle of the stacking. So if we begin on phase 2, that means it's going to load down phase 3. So we'll look then and go back to our inputs and we'll place an inductor on that phase. We know that we're going to be loading down phase 3, so when we place the inductor there, which we haven't covered quite yet, even at this distance, the inductors are picking up amperage, and we have 4.3 milliamps on the back inductor, 5.2 milliamps on the front inductor, and 3.8 milliamps on the inductor placed to the side. Go ahead now and start loading the system down. And we're going to place that on the top coil of phase 2, which is going to load down phase 3. So we'll focus in then and look at our amperage and stator change when in fact we load down phase 3. Phase 3 is currently fluctuating between 1.7 and 1.9 amps. We're going to place that over there. And we see we loaded down phase 3. We're going to do the same thing now with phase 2, or phase 1 probably. And we should see a drop on phase 1's amperage. We've got a drop in phase 1's amperage. Look at the conditions of what we just did. Those are 2 inductors placed on the system. In the appropriate change, you didn't put conditions. And now we'll finally go there and load down phase number 2, which hasn't been yet loaded down. We see 0.69 over there. Now, all phases have been loaded down. The result of this load down, with the appropriate input amperages reduced, we see 85 milliamps on the back being extracted. We see the front and the back. The front is 87. The back is 70 some. And on the third one, we see that we have procured 59, 55 milliamps. Now we're going to remove that third inductor, and we're going to look at the amperage rise on the remaining 2 inductors. These are the remaining 2 inductors, and we got a clip in our vision ray. We got 140 in fluctuation on the front inductor. We have 100 and some milliamps on the back inductor, and we're only concerned now with those 2. Now we have on our input quantities, we see that Phase 2 is the highest quantity. It hasn't been loaded down. Phase 1 has been loaded down. Phase 3 has been loaded down. Now what we're going to do is we're going to raise the inductors in space by 1 inch. When we do this, we're going to watch our corresponding amperage procurements as we in fact raise those inductors up in space 1 inch above their poles. We have 140 fluctuating milliamps. The back meter, I'm going to raise that 1 inch. Now have an increase to 170 milliamps. I want to do the same thing with the next inductor, which is at 100 milliamps. Technical difficulties here in positioning. Okay, we're looking at that. Some 94 milliamps. We're going to raise that inductor. And we have a corresponding rise. There more energy is being procured when we raise the inductors in space. The voltage, these are 7,000 ohm inductors, and the voltage that is being procured for every 1 milliamp, we have approximately 7 volts. Now, since we see that our amperage and our inductors went up when we raised them in space, we note our new inputs. And now what we're going to do is we're going to try to finish this out quickly by we're going to increase the field voltage. Here's our new field conditions. Note that the voltages went up 6.7, 6.9 on phase 1, 7.4 on phase 2, and 6.7 on phase 3. What we're going to do now is we're going to increase our field volume. We're going to take out one of the 4 ohm ballasting resistors. See if those bulbs light. Krypton bulb lighting, very sensitive to ground path. We take up, and we have Xenon bulb also lighting. That's the ground. Very sensitive to touch or the interference. Formally, these demos were done with the stronger field and full range. Since we have noticed that we procured more power away from the inductors, we'll now quickly conclude then by placing the inductors straight over the poles and noting that the bulb discharge will be diminished. Krypton bulb. Xenon bulb. Note that we did receive less power closer to the poles than we did away from the poles. And here's our new input conditions. Thank you.